Hello, Maurieo! In this video, Maurieo calculates a curve. And here's the curve, hidden here amongst all of this material and calculations. So here's our curve here, 43 degrees 15 in here like so, and 152.48 this way. 44.68, that's the radius there, centre line of a curve. So just before we get started, I look at this diagram and I look at all the things I can work out. First of all, looking at these here, the radius is always at right angles to a tangent. A curve always starts at a tangent point. So round here is have the arc going from tangent point to tangent point. So the radius, these are always right angles in here. They're the radii. So straight away there, and we've got these bearings down here. So when we look at a bearing, the best way I want to work out this angle in here. The best way is to have all of the bearings going away from you, and so that you can work it clockwise. So I'm going to use 1/5 or anti-clockwise, it doesn't really matter. So here I've got 223 degrees 15, which is 180 different to 43.15 going in that direction. So 223.15, 152.48 is definitely going in that direction, so they're both going away from me. 223.15 minus 152.48 gives us 70 degrees 27. Okay, so that there gives us our angle here. Now, with various equalities and things to do with these trapeziums and what have you, I think we'll find that the central angle here will be 100 opposite angles of a quadrilateral add to 180. So if that's 70.27, this one here will be 180 minus 70 degrees 27, which is 109.33. But I've also worked it out from the bearings as well. Given that these tangent radii are right angles to the tangent, if that's 43 degrees 15, then that must be 90 plus that, which is 133.15. If this here is 152.48, then we add 90 to that, 242.48, which gives us these bearings in here. So now we can work out the central angle. We've got the bearings, but they're sort of not in a favourable way. If we try and calculate the angle around this way, we have to go past 360. That makes it a bit difficult. So I've just drawn a little angle out here. Remember that opposite angles are equal. So I've got that bearing going out there at 242 degrees 48, and this one going out here at 133.15. So they're both going away from the centre of the angle. We can take them away now. 242 degrees 48 minus 133.15 gives us 109.33, as I predicted up here, because the opposite angles of a quadrilateral add to 180, as you can see here with the 90 there. So at this point in time, that's sufficient. We have sufficient information there to calculate the arc length. We just need the central angle and the radius. Now, the circumference of a circle is equal to 2 pi r. That's the full 360 degrees. The circumference being the perimeter, or the distance around the outside of the circle. So 2 pi r, and that's the same for every circle. No matter how big or how small, the formula is 2 pi times the radius. Amazing. So the arc length of BC is only a fraction of the total length of the circle. So the total circumference of our curve here would be 2 pi times 44.68, the radius. And we just want that fraction of it subtended by the angle, the central angle, 109 degrees 33. And so we put that over 360 degrees, which gives us the fraction So there you go, 109 degrees 33 over 360 degrees times the circumference of the circle, so the fraction the fraction of the circle that the arc represents times the total circumference of the circle, and that works out at 85.429. So moving on, we now want to measure the chord length BC to EC. So a chord is any line that goes from any 2 points on a circle. So here we got BC to EC. That's the chord of that arc. There is of course the diameter, which is essentially the chord that goes through the center of the circle. But we can draw any line from one side of the circle to the other, and that is called a chord. C-H-O-R-D. Now we want to work out the chord length BC to EC. So the first thing I've done is to draw in the chord, and then we can see where it is. We can see that we get a triangle here with the two radii, and we've got the angle at the middle there. That's not a right angle triangle, so we could, if we wanted to, we could work that out, but there is a slightly easier way using the symmetry, and I think I've got one M, symmetry. I've got that. Possibly there should be another M in there. I may have spelt that incorrectly, but I'm sure you'll forgive me for that. So the other thing I did is draw in this line here from IP to CP. Now they will those two there will cross at a right angle, and we'll see here that these two distances, it will also cut the angle in half. So for a start off, I halved the angle 70 degrees 27. I over here calculated what half that is, just dividing it by 2. 35, 13, 30, 35, 13, 30. I also cut this angle here in half, because that's what that line does, and that gives us 54, 46, 30 for these two angles here. And then we can see with various other features, if that's 35, 13, 30, that will be 54, 46, 30 in here, 90 minus, I just might, while I'm here, just put a little minus sign in there, if I may. Yes, 90 minus that gives you 54, 46, 30, and again these add to right angles. So we can see, you'll note that this is an isosceles triangle because the two sides here are the same. We might just add a little bit to that there as well, just indicate that that side there and that side there are the same, and of course they are the radii or radius of the circle. So quite a lot of information there. I've also labelled this point here X and this point here Y, just so that we can get a few things out. So quite a lot of information there by just drawing those two lines in. So calculate the chord length. Well, the chord length we can calculate from BC to X just out of this little triangle that I've taken out here, and BC to X is 44.68 times sine 54, 46, 30. So that works out quite nicely. Sine is opposite over the hypotenuse, so quite simply we can work that out, and we get 36.499. Noticing of course that these two sides are equal, both 36.499, so therefore our chord length is 2 times that, which is 72.998. I should also remind you that when I was working through this problem, I have the problem, initially I drew the problem up to put it here in AutoCAD, so I could continually refer back to AutoCAD, and by clicking on the properties of the various lines, just check that the answers that I was getting here are the same as what I was getting in AutoCAD. Just, yes, once again here I've put the the symmetry in there. I could have spelt that wrong. Radius in here, and remember that the angle between a radius and a tangent is equal to 90 degrees always. So that's why it's very important when you're in a situation where you're setting out circles and curves and things like that, circular curves, that you know where the tangent points are, because these give you some important facts about the geometry of the various circles. So moving right ahead now, we are going to move on to the central angle. Now, I calculated that earlier and showed you how to do that, so I thought that was one of the first things I did, probably because it was just there to be calculated. So it's quite simply obviously you can work out the bearings of the various bits and pieces, the radii, working out those bearings, and then I showed you in the previous slide there how to take them away to get the angle 109 degrees 33. So yeah, anticipation there, got ahead of there. Now the tangent length from BC to IP generally standing for the intersection point, or the IP of the two tangents, and that's a bit of a common terminology there, sometimes used. So the tangent length is BC to IP. So just using this triangle here with the right angle in it, that's the BC CP IP triangle. I've added the red information to help with the answer to the next step 5. So I'm just using the green triangle. I've put in the we've got the angles, we know that it's right angle, and we've got a radius here. So very simply, tan of 35 degrees 1330 equals 44.68, which is the radius, over the BC, the tangent length that we want to calculate. So the tangent's length will equal 44.68 divided by tan 35 degrees 1330, which gives us 63.279, which I've written here on the diagram just to add further clutter and confusion. I like to have the answers on the diagram. I've chosen the different colours. The next thing we need to work out, or we can work out, is the chord to arc separation, also known as the middle ordinate. Now, this is the difference between, this is the distance between the chord and the arc, xy. Very simply, we know that the radius, CPY is a radius, 44.68. So if we can calculate CP to x and take that away, that'll give us the chord to arc separation. So very simply, I think I've pretty much explained it there. Cos of just using our little triangle here, I've drawn in the red there. We're going to calculate CP to x and then subtract that from the radius to get xy. I just might, just while I'm here, just use me red pen and oops, see if I can't, yeah, there we go. Just put that in there. Oops, not quite cooperating. 18.909, which is what we calculated there, and in here 25.771. Okay, so yeah, we calculate CP to x, 44.68 times cos 54.4630. And that gives us 25.771, which I've shown there, CP to x. The radius minus that, 44.68 minus 25.771, gives us 18.909. And there we have it, 18.909. The chord to arc separation, also known as the middle ordinate. Well, there you are, one curve calculated. Look forward to other curves being calculated in perhaps maurieo CALCS A CURVE 2.